Hello, sir.
Hello. Niaz Ali Khan. Okay, thanks. So we will start class now from here. So if you still have any question, you can directly text me or just in the chat box. I will look on it, and during the class you can ask the questions to Professor Timo. So okay, so I will invite now Professor Timo to please, you can start the class now.
All right, Zishan, thank you. Let me start with sharing my screen, but you have to allow me.
Recording in progress.
You didn't allow me yet. Okay. I got it now. Okay. Okay, so, and I hope you all can see my screen. So welcome back, everybody. Great. Okay, welcome back, everybody. So we had a few days break now. So let's go back. Let me see. Right, and let's start like always with questions from last time that I didn't answer last time. So, okay, that's a good one. Can you explain the reason to use ascending, descending orbits in the INSA? So yes, sure. Okay. So why do we use that? And the main reason is in interferometry, what we do measure, okay, we measure deformation, but we measure deformation only in one direction. So we measure deformation like in the direction our sensor is looking, okay. So if we measure any millimeter motion, okay, this is measured in this line of sight direction, the LOS direction, that stands for line of sight. So if we have one orbit, if you're looking for one direction, we only have a one directional measurement. Okay, so we know, well, there is some motion. A motion goes away from the sensor or toward the sensor. But we don't really know if we have a subsidence here or horizontal motion. Okay, because let me choose another color. So if we have our point on the ground, it could move in this way, right? Or it could move down, right? Both of them would lead to such a motion, as this arrow here shows. Both of these motion would lead to such a motion in the line of sight direction. So we don't really know in which direction our ground is moving. Is it moving to the east, or is it going down from one orbit, from one direction? We can't really distinguish that, right? So you can then start to assume, for example, very often people go and say, well, we assume it's subsidence, so we assume it's going down. But we start guessing, right? You start assuming, you're not really sure. Now, if you have the opportunity to have a second measurement from another orbit, ideally from the opposite orbit, so that we have an ascending and descending orbit, now you get a second measurement. And again, you can then see where, in which direction, right? Is it in this measurement, right? And then you can separate the different motion vectors. You could say, well, if it's like I painted, we have also a downward a motion away from the satellite here in the second orbit, and it's clearly a downward subsidence here. So by having two measurement directions, now you can move toward a two-dimensional, where you can get a two-dimensional measurement. Actually, as they're not 90 degrees to each other, they're slightly tilted. You get a 3D measurement. Actually, you can get to a 3D deformation vector for each point, as long as you make sure that you from both orbits look at the same point. Then you can separate these measurements into a 3D motion vector, and so you get much more information out of that about the nature of the motion. Like, is it subsidence or horizontal motion? And that's very often important for different application, because that can mean different things, right? If we have a subsidence or horizontal motion. Very often, it's very common though that you see both, right? That you see some form of mixture between subsidence and some kind of horizontal motion. Imagine, for example, a landslide. If you have a landslide, you're gonna have a downward motion, and you're gonna have a horizontal motion component, okay? Because it's not, falling down directly. So having mixtures of horizontal and vertical motions is the norm, and by having two measurement directions, we can separate those. I hope it was more clear again, but we're coming back today again to that with some more examples. All right. If you have an artificial corner reflector, well, and that's going to act like a PS point, right? You're right that it's going to be a point scatterer. It is, it's stable in that sense. It's going to have the highest reflection, right? Can we, as a PS point without using at least 20 star images, right? Yes and no. Okay, but right. So first of all, this is a measurement that has its own name. Now, I think it's CR INSA, or I think CR INSA for corner reflector INSA, and there's also stuff written about it. Now, what we do with that? Now, first, we probably do not need 20 SAR images there anymore. But why do we need so many images? Because we're going to have to separate the different influences. So let's take a look. What are our interface components? Okay, so you have your corner reflector, right? So we can, it's no problem. We can solve for the flat. You probably has a good measurement of the position of your corner reflector. You could solve for elevation. Okay, we will have, there's always some terminal noise, but we will have less noise. However, you are interested in displacement, okay, but you did not get rid of atmosphere yet. Okay, that's still there. Okay, so you're not totally solved all your problems. Also, let me go back to the slide before. So, it's not, now it's going back. Okay. All right, so you set up your corner reflector here, okay? You're not going to get a measurement that you can use for that out of two images. Okay, out of two images, you get one phase difference. It's not going to give you the motion. You're going to need at least three, okay, to get some measurement out of that. And one corner reflector is not going to do it. So if you remember, for PS INSA, we select these points, we select these PS points, okay? And we connect them, because what we actually do measure in INSA is always a difference a relative difference. So that means a difference from one point to another, from one pixel to another. So we measure differences in height between 2 points, or differences in motion between 2 points. So if you only have one corner reflector, you can't really do that. Right? So you would need a second corner reflector. Okay. Now you can link them. You can connect them, and you can differentiate the phases between them. Okay. And now you would need to assume one corner reflector is stable and the other is unstable. Right. You would say one is not moving, the other is moving. However, you can come to this assumption is up to the test case, but let's assume you're interested in landslides. You're setting up a corner reflector, so you already know where is the landslide. So you could set up one outside of the obvious landslide zone and one inside the landslide zone. And then you would look at the motion difference between these two. Right? And yes, you wouldn't need to actually solve for much of that, but what you have between these two is still there is a difference. Oh, I have to paint again with my mouse. I don't like that. A difference in atmosphere. Okay. So you have a difference in motion and a difference in atmosphere between these two. To be able to ignore that, okay, you can ignore the atmosphere if these two corner reflectors are close together. Okay, if you say they are, let's say, less than a kilometer, the number we use is 2 kilometers. They're less than 2 kilometers apart. Okay, so the changes caused by changes in the atmosphere, the difference in these 2 kilometers is very small. We can basically ignore them. And then you can do that, right? And then you need not 20 images anymore. You could do with 3, right? 3 or more to go over time to get them. Okay, so yes, right. That would be a way, but the difference is not really that they are corner reflectors that you set up. The difference is a bit more that you just use 2 points and you connect them and they're close to each other, and you know one point is not really moving. Right. Otherwise, you can also you can set up your corner reflectors, and they will be found as PS point, and you can have them in your complete network. Remove the atmosphere with them and go through the differences. So there are different ways to approach that. But yes, if you do that, it's a little bit easier. You don't need so many images, but you would need at least two corner reflectors in relative proximity, which is not going to be a huge issue if you're interested in local motion like a landslide. There you can, you can set up 1 kilometer, 2 kilometers away on a rather stable area. That should be doable. Okay. Can we use ALOS data for processing stems on Snap and MATLAB? As far as I know, yes. Okay, I can't really comment on all the different software tools, but I don't see why not. I think that should be, as far as I know, that this should be no problem. Okay, how did we get the magnitude of the motion in Mount Etna and all the other examples, right? So at the end, right, we, as just said now, we connect 2 points. Okay. Then we connect many points, but between 2 points, right, the difference is then estimated. You see there would be the motion that is estimated, right? we have also the height that we solve for. So we have basically two unknowns here, the height and the motion. We have a bit more unknowns because the number of unwrapping cycles for the topography and for the motion are also unknown for each image. So we have always more unknowns in that solution than actually known. So it's always a underdetermined system. Nevertheless, that is solvable. For example, you can go and at the end, what we're doing is we minimize. There are different methods to do that, but we minimize for the residuals to have them minimized in the set of equations. So overall, we can then find a solution for the linear motion or the height in that set of equations. One way to do that. The standard Pearson server is using a periodogram function to solve for that. Another way, which we also talked today, I think, about, is to use the fact that A1 and B1, or A1 to AN, B1 to BN, these are definitely integers. So you can, something about these values, you can work with that by using then an integer least squares, solving the lambda solution for that, and then you can solve these equations. So that's part of that, right? How we get to the motion and the overall process on how we remove the atmosphere. And how we come up at the end of that, I explained last time already for a rather long time. So I'm not going to go over everything again. Okay. Right. If we study an unstable area like volcano, right, where should we choose the reference point? Right. And the reference point must be stable over period as much as it can. Well, the reference point as such must not be stable. Okay, that is, right. Sorry, wait, let me go back. I don't like the word must. Okay, maybe should is better. Okay, because it doesn't really matter if he's stable, in a sense that everything you are measuring is relative to that reference point. Okay, so if your reference point is moving, let's say your reference point is subsiding. Your reference point is going down 10 millimeters per year. Okay, so all your measurements will be relative to that reference point. So if you have a stable point, that would be now go 10 millimeter up, okay? Because relative to that reference point, he goes up 10 millimeter. Although in actuality, the reference point is the one that is moving. That's not gonna be, you need to be aware of that, right? That's point number one. You need to be aware of that your measurement is relative to the reference point. But beside that, for most analysis, that doesn't really matter so much, okay? Because, well, now all the points go, if you assume most of the points are stable, now most of the points go 10 millimeter up. When you analyze that, you will be able to recognize that and filter that out with your eyes already, right? Like by looking at it. It's not such a huge problem if your reference point is moving, because in reality, everything is moving. Okay. What your reference point should not do is shaking. That means he should not, have some kind of unstable motion. Okay, because then all your measurements are just messed up. Okay, if he's stably, slowly going down compared to the rest of the points, it's not such a huge deal. Nevertheless, well, you should try to find a rather stable area, and that would be, probably not on the volcano itself. Okay, that would be number one choice. Okay, but do not get, too worried about that. If your reference point is also moving, but we are not doing in any way, one has to understand, we are not doing any absolute measurement. It is always relative from one point to another in some way. Okay, so it is always a relative measurement, and if your reference point is itself moving, you will still see we are looking at differences in motion over the scene. So, you will still identify the difference of other motion components over the scene, even if your reference is moving. So that's not gonna be a huge issue in analyzing. It is a bit of a problem if you think you have absolute measurements, or if you want to move them to absolute measurements via some other, including some GPS measurements or something like that, then you probably need to take more care about that. But in general, we anyway analyze them as relative measurements and can accept that our reference point is also moving. Of course, again, typically it always does move as well. Yeah, that's a good point, right? So, because we talk about, and just now again, right, we talk about a stable reference point, a stable PS point. But we want to detect movement. So what does it mean, right? Yes, okay. That's actually a very good point. So let me try to explain that. So stable in that sense means that it is not shaking, okay, but moving slowly, okay. So let's take a look at such a building, okay. The edges on the building, right, they form double bonds, for example, or triple bonds, and are relatively stable. They are not shaking in the wind, okay. They are not growing, okay. They are relatively stable, even if the whole building, even if we have a certain subsidence here, the point itself is stable in the sense of for INSA measurements. You have to see that in contrast to unstable, what we call unstable. These are here, it's a slide from temporal regulation, but it's something like the motion from vegetation, from trees, where we have motion that is not related to deformation, that is more like a shaking, okay, that is not in any form a linear model. So in itself, such a motion of the tree, of the twigs, they are measurable with INSA, but we can't model them. Right? We need the velocities that we can estimate. We need to be able to model them. We can model linear velocities, we can model temperature-related velocities, we can develop models based on soil compaction, volcanic activities. Typically, we model the volcanic activities based on the INSA, but we can also do it the other way around, and so on. Right? These are things that we can model unstable points is something like vegetation that is a model that is shaking with the wind, that is unstable in a sense that it's moving, close to the wavelengths or in factors relative large parts of the wavelengths, then this is a very strong motion that we cannot model. That is, then we lose our coherence, we have decorrelation, then we can't measure that anymore. So stable in that sense means maybe the best word to describe it is not shaking. Okay, so that one is, no, sorry, you don't see that. Something like that is stable. That oil rig here, sorry. Sorry, 1 second. That one here, right, that's also moving. That would probably not make a good PS point, right? Because that one is also then shaking. Okay, it is a more stable movement that in itself stays in place, and if we monitor that for a very long time with very many images and average over it, might be working. But nevertheless, that's not the part we would be looking at. We would be looking at that part here that is stable. That one, the top here, the head of that pump would also be unstable. Okay, so that is what we talk about stable points. They are stable, and then they are moving slowly, so they are moving in fractions of the wavelengths. If we have 3 centimeter wavelengths, we are actually measuring half of that, so 1.5 centimeters, so they have to move in fractions of 1 centimeter. Right. To be measurable, motions that go beyond that are then not measurable and lead to decorrelation and decoherence. So the head of that pump would move too much, as would that tree. Right? They would be moving too much. So they are not stable in that sense. Okay. Then let me go on. Okay. Right. The INSA is too weak to perform in densely vegetated area. Is highly dense vegetation also a big problem for PSI? Yeah, the answer is yes for that, and we'll come to that, I guess, today on how to work on that. But yes, that is a problem for PSI as well. However, I don't like words are important. Weak is just not the right word to describe that. Right? It does not really perform well in densely vegetated areas. And that's also a big problem for PSI, because we need these stable points. We need these PS points. Vegetated areas, they're not stable. They decorrelate, right? They're incoherent. So we can't really find points there. So we don't get the PS density that we need. We said last time we need something like 5 points or 10 points per square kilometer to get a density of points so that we can successfully estimate the atmosphere, remove the atmosphere, and make our measurement. All that we cannot do if we don't have enough PS points. We do not get stable points in densely vegetated areas. Depending a bit on your wavelengths, if you have very long wavelengths, it's going to be better. But generally, it's a problem. And that is also the case for PSI. And we will talk today, latest next tomorrow, about methods that work on that fix that, or at least improve that. Okay, but yes, the problem is also there. Okay, So just to recap, last time we talked about the permanent scatterer interferometry. Right. We are looking at different case studies. Only the one is the case of sinkholes. Sinkholes are very difficult to catch, and they're unfortunately also very dangerous because of their sudden appearance and then the sudden damage that they're causing. Now, when we look at that data, and that is one is honest, looked at the data after the collapse, one found that we can see for these three red targets here, for these three red points, there is a motion visible before the collapse. So this is here one example marked in red, and we can see the motion. The points are stable. They're stable for a long time, but then shortly before the collapse, we see an increase in velocity. And that is a very, very typical and very dangerous motion pattern. It's also typical. We see that also in landslides. We see them moving slowly over long periods of time, but when they then start suddenly to increase speed, there is then the possibility of a catastrophic landslide event that may appear. So this situation with a sudden increase in speed is often are these precursors to more dangerous developments. Now, the problem that we have is to actually identify them and separate them from noise. One problem in that is that, at least in the standard PS-INSA method, we are estimating a linear velocity. Okay, and if you would do that, let me take another example, right? If you would do that, if you would estimate a linear velocity over all these points, you would end up somewhere here. Okay, so some line in the middle, with then also large differences, especially toward the end of that deformation. When the speed increases, our differences between our measurement and our model, in that case our model is that linear velocity model, gets bigger and bigger, which means we have more residuals, which then means we have a lower ensemble coherence, or temporal coherence is what we call that. And that may lead to that we even consider that point to be not stable, not fitting to our model. We may filter that point out. We may ignore it. So the problem is, it doesn't fit to our linear model. So we may not see it. Even if we estimate it still correctly, right? Very often we will then ignore it. Somebody analyzing these points may look at that and may say, that's maybe an outlier, there's nothing to worry about. Everything is stable here. There's 3 points that might be an outlier. And that's unfortunately quite common, because if you analyze lots of PS-INSA results, outliers like that, errors, measurements that you cannot explain, they are quite common. Okay, and so it's not uncommon to ignore them, to filter them out. Let's not forget, these 3 points would have a rather low fitting to our models, or rather low temporal coherence. The software may filter them out already. The human operator may ignore them. So unfortunately, we are not there, although this, as you see, it's a very old example. And we're still not there that we would say we can automatically identify sinkholes even 20 years later. The problem is that they look too much like outliers, and the sinkholes are small phenomena. So you're gonna have 1 or 2 points in a surrounding that is stable, and that's very often then gonna be filtered out there. You know, the human operator is going to ignore that. Right, and you know, that's why I said they went and made the analysis here after the collapse. Because before the collapse, you would maybe see that there is motion, but you know, it would be unexplained. You couldn't explain it, tending to ignore it. So there is now research already also for years gone on, people trying to find ways to, for example, use machine learning to identify, to separate these very dangerous motion precursors of sinkholes, precursors of landslides, from noise and outliers. Okay, so that is not easy. That is still ongoing task, and well, also interesting research topic. Not solved yet, I have to say that. Okay. And that is, although we clearly, we can see the motion, it is clearly measurable. The technique can measure it, right? We have also methods to get to nonlinear motion. This is not, well, we talk about that today. We are not only fixed to linear motion. We can easily come to several other models, but still, these kind of local events are still difficult to catch. Now, we can measure the subsidence. This is just the example from subway lines in Shanghai. If you excavate tunnels, if you dig subway lines, you're going to have deformation on top of them, especially if you have some soft soil like in Shanghai. They will subside for some time and then hopefully settle. And we can clearly measure that here with PS INSA, that you, again, if we look at that, right, let me see, right, we see here these linear deformation elements. We can follow them nicely. But you see in the results, it's very nice and realistic results. You see, just mark some other points here, right, that might be deformation. Most probably are just some outliers or some noise on it, okay? And you see how difficult that would be to identify sinkholes in that, because it's quite common to have such outliers in that data. This is a quite realistic, you know, example here. And we can identify the subway lines clearly, but we're doing that by seeing, you know, the form, you're following the linear form, okay? But some sinkholes and some other deformations that are just of very small area, they're sometimes then hard to identify in that. All right. Anyway, we talked about that last time. Showed some examples here of strong deformation, very strong subsidence examples. And you see here tilting new buildings with very strong subsidence. We can measure that. Here also in that example, here we did the multi-stack analysis. We did ascending and descending analysis here to cover both directions and measuring that. Another example is then from Alexandria we also have building collapses. The question that was here is why, again, can we measure that? Can we have a kind of prediction or at least identify areas that are more in danger for buildings, comparing demotion to actually appear building collapses. There's not, I have to say, there's not such a one-to-one relation between both. We find that we have more collapses in areas where we find a rather complex motion. So where we find subsidence close to uplift with probably some horizontal motion mixed in. That seems to be most dangerous. It also makes sense. So if you have a larger area subsiding, it's not really dangerous for building because the whole building will go down. It's getting dangerous for buildings if one part of the building goes down and the other part goes up or moves horizontally. So if they move in opposite directions, then it's starting to get dangerous for building stability. Areas with very high difference in gradient of movements seem to be most dangerous, but again, it's not also here not a one-to-one relationship because not all collapses there are directly related to subsidence in the sense of a larger area subsidence. Probably some are just really bad built. So it is a rather complex situation. All right, that's where we stopped last time due to because we was running out of time.
Sau đáp là cộng mệnh đề.
Okay, so
nhớ chưa? Và nó dịch là đề
a bit
cái này là mệnh đề.
Step by step.
Mệnh đề.
Over the example of one software tool. There are many tools and different approaches to do that. And we will go over different tools and techniques after that.
Cộng với mệnh đề luôn.
Well, what we're gonna do? It's a long process. Okay, so first we're gonna have to import the data. That makes sense, right? Okay.
In order to thì sao?
Then we select the master image.
In order to thì cộng một infinity cũng là để mà. Được chưa? Cho nên đây chúng ta chọn A và B.
Co-registered image.
Sang câu số 2, tôi vừa mới đi đến một ngôi làng làm nón lá ở
the co-registration is to a single master image, right? We co-register it to one image, even if we later process interferograms differently. We co-register them to one image, so they all have the same coordinate system.
Chúng tôi ăn trưa, chúng tôi đi tới ngôi làng đá cẩm thạch non nước để mua một ít quà lưu niệm.
Not every implementation does that.
Sau khi đúng
không? We often do not need to process the whole interference. We can also first select the PS points and then only process the interferometric phase for these PS points for these few pixels servicing their PS candidates. That can save you then processing time, right? You don't need to process all images for interferogram. It just goes through this subset of pixels and get the face values there. That would gonna be much faster, right? So both is possible. Right. Then we estimate the atmospheric phase screen. Typically, we're gonna do that on just a subset of the PS candidates.
Rồi, câu B bởi vì
for the APS estimation, normally we have more PS points, especially in urban areas. We normally have more PS points. Then we need to estimate the atmosphere. We typically have far more than the 10 PS per square kilometer. So we do not need them all. So typically we take the best points form a dense enough network, connect these points, estimate the atmosphere based on this subset of PS points. That again saves you processing time and we do not need
cái tiệm này là một cái điểm thu hút ở thành phố của tôi bởi vì những cái sản phẩm ở đó.
And then after we remove the atmosphere, we process all the points.
Bảo nào.
Now directly to the reference point.
một cái nón lá thì được
and then we can do some post-processing. That should be, for example, some filtering. Now we're going to say, we look at the points. There may be a bit noisy. So we say, well, let's filter out all points which are not stable. We can take a look. Typically, we take a look. Do our points fit to the model that we estimate? Do they have high ensemble coherence or temporal coherence, which means are the residuals low? Right. And we keep them, otherwise we may filter them out.
Sang câu số 9 này. Bảo nào.
And then
Đây
visualize them.
Nón làng chương.
Visualize them to
vì nó được
put them on the map. Show them in 3D, show the deformation, whatever you choose to
Sin là vì, sâu là vì thế, đừng có nhầm lẫn nhá. Rồi như
best
có
be
10 con.
able to visualize it in a way.
Làm nhanh lên.
But for your audience,
bởi vì họ có rất nhiều sản phẩm, họ làm một ít và những người khác làm phần còn lại là rest. Câu 11 chọn gì?
There can be, that is not so trivial.
Câu 11 là cứ nói này, lúc for work to anh bảo nhớ nha, Nhi đã nó làm nhiều lần nó nhớ hết rồi. Lúc for work to cộng động từ thập in, cho nên con chọn câu này. Nhanh lên để sang cái đề khác vì đề này nó quá quen thuộc đi. Nó là một cái nơi tốt để cho những ai mà yêu thiên nhiên và yên tĩnh. Đây chính là for those. Rồi câu tiếp theo này, bạn thích lịch sử vì thế bạn sẽ đến vì thế Việt Nam bảo tàng gì? Lịch sử Việt Nam là một cái nơi phải đáng xem must see.
The master image in the middle.
Rồi sang câu số 14 này, những nghệ nhân
normally
đã
we would also
đổ
co-register our images to that image.
Bằng đồng, đúc là KHØI. Rồi câu tiếp theo, sống dựa vào nghề gì đó là live on.
Co-register them to another image that you formed interpolograms so that is possible. That can lead to extra errors.
Có một cái gì, có một bộ sưu tập về đồ thủ công á, được làm từ những ngôi làng thủ công khác nhau. Bộ sưu tập chúng ta đang cần bộ sưu tập danh từ collection. Collector là nhà sưu tập không chơi. Câu số 17 vào tuần trước chúng tôi đã có một chuyến đi đáng nhớ tới một sở thú mới ở trung tâm thành phố. Bây giờ chúng ta trung tâm thành phố chúng ta có này, in the center rồi in the center, phải là phải in ở đây có on rồi, chúng ta xài câu đầu tiên là outskirts.
That mass image, so we have basically that gives us
rồi câu số 18 này,
the minimum number of
sau đó thì chúng tôi đã có một bữa ăn trưa ngon lành mà được chuẩn bị bởi ngay vào
save processing time in case of yes points.
Rồi câu số 19,
additional interpolograms would be redundant, they're not necessary. When we talk about that in alternative approaches, so such we call it the star, the form star interpolograms. That is the standard in PS.
Câu 21, thành phố gần đây đã xây dựng một cái thư viện nha, thư viện xây dựng là set up này. Rồi câu 22, triển lãm cuối cùng thì không thú vị bằng cái này. Bây giờ so sánh không bằng và chúng ta sẽ chọn là so interesting as nè. Rồi câu 23, tôi không nghĩ rằng Fred hòa hợp với Daniel, họ luôn luôn cãi nhau, hòa hợp có mối quan hệ tốt với ai. Câu 24, thành phố này đang phát triển nhanh nhất cho phép so sánh nhất cộng với tính từ thêm Esther. Câu 25, bạn nên cởi mũ của bạn ra ở trong đoạn chiếu phim cởi ra sẽ là checkered. Okay.
Do some cross correlation. Okay,
bạn không phải là một tài.
Nowadays with good. Nowadays the images, the satellites have good orbit coordinates, so we use the original orbits. The images are already pretty good co-registered. Okay, if you only use the orbit information, and you choose a set of image chips, I don't know, 400, 800, something like that, small chips over the image, search for the best fitting. Right, what is the best fitting combination? Where do these small image chips fit the best in a certain search area? You can do that then in sub-pixel accuracy, right? And then you just go and estimate the parameters that you need for your resampling, the resample parameters, and because you're gonna have many more small image chips then you actually need to estimate the parameters. You can then go typically over some repeating process. You throw out the worst, the image chips, pair of image chips that fits the least. Okay, you throw them out, and then you go again, estimate new parameters, search the worst one, throw them out until you reach a threshold where you are satisfied with. That works pretty well. The co-registration of the images, EFSA images, even to less than 0.1 pixel, even with hundreds of images, typically works very well without much problems. However, problems can occur. That's why I wrote the last line. Strongly suggested to check the results and to, if necessary, adjust the parameters because errors can occur, especially if there are changes on the ground. So I don't have that example here. Give you an example, okay, but I don't have the example image here, but we have that later. Actually, that scene here, we look at the interferograms, the Las Vegas scene I also showed you before. There is actually co-registration problems in that scene can occur, and that is because you see here these parking lots, right? Okay, these are parking lots, and there are several huge parking lots in that scene. And well, them being parking lots, they have cars on that, and the cars, they have a very good, contrast to the background. So the cars are very white, and the parking asphalt, the roads are very black. So they're actually good for co-registration. And it's sometimes then the computer, they find very good contrast in these parking lots and match them from one image to another. And that's not good. It's not good because, the cars are parking differently each time, right? Often, if the parking lot is full, they look like the same, but sometimes then they park differently. And that can, for example, actually, in that case, it did lead to misregistration, right? Because if he's focusing too much on parking lots, cars park differently. So that's can be a problem. Another example that we had, I don't have that image here, but it's more on, there was northern of China, grassland. There is not much contrast in the scene, but there's a river going through that scene. So you're looking for image chips, you're looking for points that you can match one image to another. That's typically you're looking at edges, right? So lots of them, of these stable edges, they will be at the river. Now the problem of that scene is that this river is a natural river, so it is meandering, it is changing its path over time. Now if you match your images to a river that is changing its path, that's not good. Okay, so that can lead to errors, and also did lead to errors there in that case. So you see, that can be things that can happen. Okay. Normally, software may give you a warning on that. It's not uncommon that users do ignore these warnings, do not see them. You have to understand when you do that for PS-INSA, you're processing 20, 30, 40, sometimes 100 images. Right? You may not scroll through all the or read all the log file information. And the way also why I talk so long about that is also this scene here, because it's a quite an old example. And if we look here now, we see the interferograms, we form the interferograms between them. And when we process the data, where is it? I think it was this one, this interferogram here. We saw that there is something is not so good in the process, and something didn't go right. And then, so we identified that interferogram as somehow being strange by looking at it. And the student who was processing that, he also found out that at that time of that image, when the image was taken, there was a sandstorm in Las Vegas, so we assumed it's bad weather situation. However, at the very end, we found out that image was maybe because of the sandstorm, but anyway, that image was not co-registered correctly. There was a registration error in the image. So at the very first step of the PS-INSA processing, there was the error already. And it took a very large time to find that error, right? Even analyzing the interferogram, studying the weather situation, all of that. At the end, it was just a co-registration error at the very first step, which is the reason why I mentioned that very often. Do check these things. They are at the end very difficult to find. If you have a co-registration error and you're not fixing that, at the end, you're probably not going to find that error anymore. All right. Okay, after that, we selected PS candidates. So, yeah. We later talk about that in more detail about the different methods, but there are different ways to do that. So in the standard PS-INSA, we are looking at the amplitude stability. So we are looking at pixels that are bright, that are white, and stable over time. So we do not need interferograms to do that. We can only do that on the based on the amplitude, and it works very well for urban areas. Because if we have a very bright point, if you have a very strong scattering, and if that scattering is stable, if the amplitude of that is stable, the phase is also going to be stable. There is a good relation between amplitude stability and phase stability. We are interested in phase stability, but we are looking at the amplitude stability because it's easier, and for strong reflecting points, the amplitude stability is very closely related to the phase stability. So for these points, it's working very well. But it's not the only way. We could look at others. For example, in stems, it's another method I will talk about them more. We're looking more at the coherence. We looking actually, it's not actually totally correct. It's not totally wrong, but it's actually at the phase stability. I should write here. It's more correct term. Sorry, there should be phase. All right, we're looking at phase stability, which is more difficult to do than amplitude stability. But at the end, we're interested in that, and that if we're doing that, we can find points that are not so bright, that have not so strong reflection, but that are coherent, that are stable, that are phase stable over time. And that also can include more problematic PS candidates. It is better suited for rural areas. Again, all right, let's put that here. It is best suited actually for volcanoes. Okay, that would be the best term. I will explain that a bit more later. I hope I wrote that right. There's a C missing. Okay, is that even right? Please excuse me if I'm without spell checker. I'm lost. Anyway, volcanoes. Okay, because on volcanoes, we have a lot of, often we find a lot of rocks, not so much vegetation, okay? We find stable points on these rocks, but they're maybe not so strongly reflecting, but they're still rather stable, right? In rural areas, it's not the best word here because there's typically vegetation. And if you have vegetation, we just don't have actually PS points anymore. So actually for stem cells, it's not really very well suited for rural areas because that still implies vegetation. It can be good for rural areas in terms of grassland, grazing areas, herding areas, where you have a very thin vegetation, not really like wheat fields or something like that. That would be too strong in terms of vegetation. Anyway, we come to that. There are different methods to do that. That's the point of these slides. There are different methods to find PS candidates. Right, and then you have to set a threshold. Okay, so, the typical threshold for the amplitude dispersion index would be something like 0.25. Right. If you set it lower in case of the dispersion index, you will have less points. If you set it higher, you will have more points. The standard is 0.25, but depending on your scene, you may choose other thresholds. Okay, it's always a bit. It's never that clear, right? I mean, if there would be one always correct threshold, the software would not let you choose. If you have lots of images over a long time, you may also set a different threshold, and then you have only a few images and so on. So it can be useful to check what happens if you change the value, see how many points you get, if that is something that is suitable. All right, and now this is just an example from one software that is actually, that one is POS actually, but there are different tools available. That one has a very, especially, let's say, ugly graphical user interface, but gives you lots of options. Right. And then we are estimating, we are selecting these points, right, over in this case here, and the amplitude stability index, which is basically the inverse of the dispersion index. Then we create a graph. So we are, if these are our PSC, we create a graph by connecting them, right, from one point. We then form then here connections between them. And then we estimate, for example, linear trend and height between a certain parameters range. That was because here is the periodogram approach is used. And estimate that, and at the end get to the estimation of the atmospheric phase screen, which will then be removed. Right. Okay. And right, so you see right here, we see the points, we form graphs between them. We then see the coherence, that is in this case the temporal coherence, which means the fitness of your points to the model. We can then see is that a good fit for these connections or not. Do we have most connections have a good coherence or not so much? For example, that's a very good example here that I show here. If you would have I don't know, if you would have a peak, you know, more here in that area, that would be not so good. That can then be an indication that, you know, maybe your linear estimation, maybe the estimation of linear motion is not correct, that there's, the points are not well connected and so on. It is then something to look at, you know. If it does not look so clear like here, then there is something wrong, gives you the chance to fix that, to probably connect them differently, to estimate their values in different parameter set and so on. So that gives you here the opportunity to change it. Then the atmosphere is estimated. We can also look at the estimated atmosphere. And then a question that typically comes up, right, is, because it is suggested to look at the atmosphere and see if the estimated atmosphere looks correct. But how would you know that? Okay, like how, you know, how does an atmosphere look like? The APS actually, how does the APS look like? Well, and the answer is something like that. So we would expect it's something, you could say this looks something like natural, like a cloud. So by that I mean, what we see here, these, you know, unclear borders, right, some lines like that. That is not so bad. What would be bad if it would be, for example, something like these lines, if the colors would change here along one direction, which would we call a phase ramp, that would not be natural, right? There would be indication for another error, right? If it's directly all in one direction, all directly in range or all along azimuth, that would be rather strange. And then actually, if you look at many atmosphere, right, for these different times, you see this is given for a certain time. It should look different. It should more or less look always different. Okay. For example, if you have, let's take a look. If you have that point, and we would go through all of them, and you would always have such a structure here at the same point. That's then an indication that something's not correct. Okay, because for an atmosphere that would be strange. It should look basically different each time. But it takes some experience, you know, to go over there to see what looks normal and what does not look normal. That is something which comes a bit from experience. I always try to explain it should look like a cloud. Okay, a little bit cloudy in its form. I think that makes also sense in terms of why we're looking at a value from an atmosphere. All right, and then we, after remove the atmosphere, we can estimate the height and motion differences for all the points, and again can take a look at the histogram or the spatial distribution of the coherence values to see the quality of the estimation and how well it fits to the model. Right? And then we can see the height information and velocity information for each of the estimated points. This is not very nice in terms of visualization. It's not very clear. So there are then other ways also to put it out in a map, right, on a GIS or whatever, Google Earth, to see the results better. But that is the overall processing step, okay, in terms of software. But there are different software tools and they have different masks. They give you, some give you more options to choose from and some have less options to choose from. So that is just one example. Okay, so one point that we had discussed is the ascending, descending analysis. So let's take a look a bit more in detail on how we can do multi-stack analysis. All right, so this is one example here from Badung. Badung is a small town upstream of the Three Gorges Dam in China. So after the dam is being filled, the old town of Badung is now underwater, and it has been moved up the hill. There is a new town being built there. And if you build a new town on a rather steep hill, what you're going to have is motion. So the question that comes up is how much, okay? And so that is very important to monitor that and to see if you know, if there's any danger to the new urban area, the new settlement area. Now, right, we have here, I think one, we have, right. Anyway, we have here 3 images, 2 ascending ones and 1 descending one. Okay. So we see certain deformation schemes. You see them, for example. So we see them here, okay, deformation. In that we see it also here, in that image, in that stack after processing. We see deformation. Here we see not the same thing. So you see, looking from different angles, processing different stacks, we may get different results. It's not, but it's common if we get different results. It's not even not uncommon, it's rather common. And there can be physical reasons behind that, and there can be just, you know, process differences. Anyway, what are we measuring again? So we are measuring this line of sight deformation. So we're measuring the deformation in that direction. Now, if we have a second direction, right, then we have 2 line of sight direction measurements. And if we combine them, then we can separate. Actually, we can go down to this 3D motion vector, but at least we can clearly separate between horizontal motion and vertical motion. Right? And so if we just visually analyze that, okay, we can say, so typically we say if a value is negative, the motion is negative, normally it is defined as moving away from the sensor, and positive moving toward the sensor. Be careful, it's not always the case in all software packages, but typically, okay? I think nowadays it's a standard to define it like that. All right, so let's choose a different color. Okay. So if we have, let's say if we have a subsidence, okay, then motion vector number 1, right, will be something like this, okay, going down, negative value. Motion vector number 2 is going down, negative value. So if both, looking from these different directions, if both have a negative value, you're going to have subsidence, right? Because both are moving away from the sensor. If both have positive values, you're going to have uplift because both moving toward the sensor. But if you have horizontal motion, what's happening with horizontal motion? Right? If we have motion, let's say we're moving in this direction, okay? So the first sensor, he will go down, right? He will have a motion in this direction because it's moving away from the sensor. But the second one, he will have motion toward the sensor, okay? So if you have one orbit, one ascending or descending negative and the other positive, then you have horizontal motion. Okay, because one is moving away from the sensor, but it's moving toward the other sensor. Okay, so it's a very simple way to just visually analyze that. You can also, in a couple of slides, we come to that, how we fuse them and then actually come to, 3D motion vectors much more better. But just visualizing, just looking at the results that you processed separately from both texts, you can just see, if both are negative, well, you have subsidence. If both are positive, you have uplift. If one is negative and one is positive, then you have horizontal motion, right? So a very simple way to separate that very quickly. All right, so if we do that and analyze that here, you see, we have here, in this case, Still-Badung example, here, in this case, the Allos pulsar data, one from a descending orbit, one from ascending orbit. In the descending orbit, if we go right in this area here, you see in both areas, it's negative. So it's a subsidence here. You can identify that very clearly. However, in the town area here, we have here some kind of negative motion. But here we can't really see that, or we have positive motion. So it is a little bit, how to say, all these points here, many points are rather blue here. So we're not really sure if we see any motion here. So is it horizontal motion or do we have an error here? It's not that clear, okay, from that example. What we can do, what we did in that example is to add another set of data, get another information and add an NVSat ASA image stack here. So again, if we look at that landslide side actually here, we see subsidence, we see negative motion in all images, so we can clearly identify this as downward motion. And now we have that side here. We don't really see it in the ascending ALOS pulsar data, but we see it in the ascending NVSat data. We see something here, there is some motion here. So there is most probably a subsidence, but also with probably some horizontal component with it there. So by just very simple visual analysis, we don't really merge these results, we just visually analyze them. We already can get quite good information. Also, it's a very realistic example. You see the middle results, the ALOS pulsar, the ascending orbit, we did not get so good and clear information. And that is also the reality of that it sometimes does not work so well. Okay. All right. Let me clear that and move on. All right. Okay, but if we want to really fuse these points, if you want to really come to move one step further than just visualizing, visually analyzing it, really fusing the different orbits. That is not that simple, okay? Because we process them differently. Okay, both data sets are processed differently. They have then also a different reference point. So they are then the heights we define them. They are set to a different reference. Okay, if our both reference points are not at the exact height, so are all of our orbits shifted. Okay, that means that also. Let me show you what that means. In the left example, You see the red points are from one orbit ascending or descending, I don't know which one, and the green are from the other direction. And they are shifted, right? They're shifted between each other. That is because if they don't have the same reference point at the end, we have a different height estimation. Now, when we geocode our points, we talked about that in the very beginning, like the height of the point is important for knowing the height of a point is important to geocode it correctly. Now, if we have a shift in the height between the two orbits because of a different reference points, that leads also to a shift in the geocoding between them. There can be a very small shift and there can be a rather large shift, depending on, how big is your difference of the reference point and the resulting shifts in geocoding. So if you want to do that, we can do that. We can correct for that. For example, we can project them into a similar coordinate system, put them into a grid. Important is the part that we need to, if we have an urban area, right, we need to remove the facade points, right? So if you have a building, please excuse my very ugly painting, okay, and we have PS points here, for example, at the windows, okay, so if we look them from one direction, we're going to see them, they form PS points, but from the other direction, if we look from the other direction, then we will not see the same building facade, right? Because in 3 dimensions, something like that. I don't know how to do that without breaking my arm. Building side A, we look at this facade. Building side B, we look at the other facade of the building. We're not looking at the same side of the building when we look from 2 different directions. So we are not seeing the same points, right? So we have to, if we want to merge them, we have to merge them on the ground points, because if you're on the ground, somewhere here in front, behind the building or in front of the building, depending where you see, right? From both directions, we're going to see the same point, even if I'm not really hitting them with my ugly painting. But on the ground, we're going to see the same point. So we're going to have to remove the facade points and just register the ground points, putting them together, right? And then we can correct for the shifts in height and the resulting shifts in the geo coordinates. Right, and then this is the unfused version, and that would be the fused version. Now they fit very well over each other, and now we can do ascending and descending analysis, because now we are at least geographically looking at the same points. And again, this is the zoom in example left, which would be before the correction, and right is after the correction. Now you see the points are overlaying each other, at least much better. You're still looking from 2 different directions, so you can never be exactly sure that you are looking at the exact same. Since typically you're looking at the exact same reflector anyway, but now at least they are spatially related, and you can match them, for example, by forming grid cells and, for example, let me make grid cell. Now all these points in that grid cell are probably the same object, right? But if I would make a grid cell here, but most of the green points would be missing, right? So now we can average them and put them together with some kind. Typically, we are forming grid sets over them. Okay. All right. So far, for the matching of different orbits, that's it. in terms of PS-INSA, now I have here a list of different software tools that you can use for sound processing. On top, these are the commercial tools. They are, they are typically very expensive even. So these are, we're talking normally several thousands of euro or something for them. But there are also free software tools available, like Roy Park or Doris or Stamps, which are in the public domain and can be used for processing, as is Snap here, for example, which many of you are using, I assume, which you can also download, as well as Snafu, which is a tool for face unwrapping, face unwrapping tool here, which actually is also used by Snap for that. Right, and then we have software that is not commercial, like tools from research organizations like the Genesis or the Epson. There are others from different universities or research organizations which are not commercial, but are also not available outside of their organization. So there are also different tools like that available. They exist. There are different tools existing. Okay, like that. Okay. All right. Okay. You can look them up. I have at the very last slides, probably then for next time I have a bit more on sources and websites and so on for you to look, and that's especially useful not here but on the PDF that you all get of them to look them up. Okay, anyway, all right. Now we talked about PS-INSA, but it's not the only way to doing that. Okay, so we have this PS-INSA, we also have some shortcomings. So we need a high density of these PS points to make PS-INSA work. And we said, okay, that works well in urban areas. But what about non-urban areas? We had a question already last time, right? We said, okay, the INSA is not really working very well with dense vegetation. What about PSI? Yeah, it's also not really working well. So what about these areas? What can we do there? Also, PS-INSA estimates linear motion. What about nonlinear motion? Right. So these are, I think, important shortcomings that have all been addressed by methods developed after PS-INSA or shortly after in some time. So we separate between two basic approaches. So we have the PS-based method, like PS-INSA. These are methods that rely on the PS points, right? So there we find methods that have alternative ways to find more PS points or find better PS points, alternative ways of processing the data. For example, also ways to include different models or just to, process the alternative approaches to that. Okay, so this would still be PS methods. And then we have the rather more different approaches, which are DS-based methods and DS-INSA, where DS stands for distributed scatter or distributed scattering. So we have PS, we have the permanent scatterer, we have these point scatterers, we have points that are stable over time, we have them as deterministic point scatterers, so we have points that then have one strong scatterer in the pixel in the resolution cell. So they're also free of speckling, right? But with DS, we have distributed scattering. We have many scatterers in the pixel. This has the advantage that it works also in non-urban areas, because now we can look for distributed scattering, which is the norm in most pixels, so we have more options to find them. But we have to deal with speckle again, because if we have distributed scattering, we have many scatterers in a pixel, therefore we have speckle effect. So we have to deal with that. And while they are suffering from spatial decorrelation and temporal decorrelation, so we typically try to limit temporal and spatial baselines for the interferogram. So we typically, for DS methods, try to have not too long time difference between the interferograms and not too high spatial difference, too long spatial baselines between the interferograms, because to avoid spatial decorrelation and temporal decorrelation, or to, let's say, minimize them. Can't really avoid them, let's say minimize them. Okay, so TS-based methods, they're going to look like that. Okay, they're going to form the interferograms from the master, and then for each of the other images, one interferogram to the master image. And we can do that because a PS, by definition, does not suffer from temporal decorrelation, so we can have, long temporal baselines like that here. Okay, it doesn't really matter, right? Because by definition, it shouldn't really suffer much from temporal decorrelation. And also we can have long spatial baselines, right? Like that here, doesn't matter, because PS points are typically formed from corner reflectors or poles, all structures that do not suffer much from spatial decorrelation as well. So we can have rather long spatial baselines. And additionally, forming in additional interferograms, adding more interferograms to that for PS is just redundant information. It is not necessary, it is redundant. Therefore, we do not need it. So this is the form of interferograms for PS-based methods. And this is going to be different for the DS-based method, for the distributed scattering. So you're going to see the difference there, and then you can learn how to separate them also in papers easily. So we have, there are more methods, right? We discuss a bit here the four methods: PS-INSA, stems, and PSP. PS-INSA we already discussed. So we're going to discuss the three other PS-based methods here, most common methods here. All right, so this is just for fun, the processing of PS-INSA without removing the APS. So if I do not remove the atmosphere, right, and just directly estimate the differences, the phase velocity and height differences to the reference point, without removing the atmosphere, I'm going to get a result like that, which is, wrong, okay, and very noisy. Contrast to the, right, this is the correct PS-INSA result, where we see some deformation in the blue marked area, right? But you see the strong influence of the atmosphere, okay? I just want to point out, this is seen in Las Vegas, so it's a desert area where we have actually a rather limited influence of the atmosphere. So if we're not removing the atmosphere, we're just getting bad. It just doesn't really work, okay? But if you're doing PS-INSA correctly, right, we get a result like that, and that is, let's say, our reference for comparison here in that example. So we see some deformation around the Las Vegas Convention Center. If you remember, I used the Las Vegas Convention Center before as example, showing you the temperature motion of the Las Vegas Convention Center. They're still in there. But what I didn't mention is that there's actually also deformation a little bit in front of the convention center. There is a subsided center there due to groundwater pumping, assumingly for the golf course. I assume that's the reason there. But not an expert on Las Vegas deformation. All right. Anyway, now let's take a look at the first alternative method, which is done here. This is spatial temporal unwrapping network. First difference would be that the point selection is based on the signal to cluster ratio. So instead of the amplitude dispersion index, the points are based on points with a high signal to cluster ratio. That works as well. It is also a very solid method to do that. Theoretically, I would say it's theoretically better than the amplitude dispersion index, but there are practical problems with it. So to estimate the signal to cluster ratio, we typically use like here the black point. That would be the point we're looking at. Okay, we then leave a little bit space, and we to left or right to avoid side lobes. So we analyze on the gray areas, the pixels in the gray areas. We take as background information. Okay, all these 4 gray areas, we would put them together to form the background, and then we form the ratio between our signal and the background, the clutter of that, to get to the SCR, the signal to cluster ratio, which is, related to the SNR, to the signal to noise ratio. All right, so that works very well. That works very well if the gray areas are representative of the background of the black pixel. That's to say, it works very well if you have a very homogeneous area, right? And the gray area is the same, all is the same, like the background of the black pixel. But that's often not the case. And especially if we go in urban areas, right, the background of the gray areas, what is in that area, might be very different from what's in the black area. So in that case, and you're using that methods, now you don't really have, you're not really estimating the signal to cluster ratio. You're now estimating the signal to some other random building ratio, right? That's not really, it's not really very good in practice, especially in dense urban areas, which again is what we typically do in PS-INSA. So that's why the SCR is not commonly used anymore. Nevertheless, it is also a good way to find stable points. If you ignoring now the problems of maybe we're not able to really estimate the signal to cluster ratio well. Then in STAN, we are actually not, and I will explain that, we actually not estimate the atmosphere at all. Right? We just densify the network later. So we never really estimate the atmosphere. And then the actually most useful part probably of STAN is using the lambda as an integer least squares estimation. Okay, so we're building that on. We're building the estimation on the fact that we have integers for the unwrapping factors, so we can do an integer least squares estimation, which can give us better results. So the stun network, the overall principle is very similar to PS insert, to the APS removal. We have our PSC points, right? We connect them one-to-one with the network. Okay, as we do in PS insert, we're doing the same thing. We're estimating the values along the edges, the height, the velocity, and the residuals along the edges. Okay, now what we do in PS insert, after we estimated the value along the edges, we are taking the residuals of those, and actually first we take a reference point, we unwrap along that, then we take the residuals of those to estimate the atmosphere and remove the atmosphere. Okay, but we don't need to do that, right? So in stun, we take our reference point, take the same reference point, and then for all of these points in our initial network, right, we get the height, like this one 10 meter, this one 20 meter. We also get the velocity for each of the points, right? While now in PS insert, we are not taking these values, we only take the residuals, estimate the atmosphere and remove the atmosphere. In stun we say, well, we already have the height, we already have the velocity, and I don't need to remove the atmosphere because now I can take each of these points from the initial network and say this is a new reference point, and I connect from each point to the closest points. Each of this connection is again less than 1 kilometer, less than 2 kilometers. Right? I just connect here to these points individually, okay, and estimate the difference along these edges again. And this time then I take the difference from these measurement points. So if I now have, let's say, this connection would be minus 5 meter, right? So I would know this point here is 10 meter high. 10 meter height here. Okay, and similar for velocity. I could estimate them all. So in stun, we are not estimating the atmosphere and we're removing it. We are following along these edges, right? And then we just densify the network to include all the points later on without actually removing the atmosphere. So that works also well. And I have here, I have to remove the annotations. You see we get comparable and similar results to PS insert. We see here a little bit a larger error, and that is also because I didn't probably not implement it that well. It doesn't matter. The problem is if you have in that network, if you have an error in your network, if there's one connection wrong, or if you have one of these reference points from the initial network is wrong, and now you're connecting to all these close other points, such errors, they will propagate through your network. Now this can also happen in PS insert, right, that you have error propagation, but it's a little bit mitigated that you at the end you look only at the residuals, you have then your atmosphere and you still filter largely over the atmosphere. So some smaller propagation errors in PS insert, they are easier mitigated, they're easier reduced, while in stun such errors can lead then to larger errors and outliers. However, right, in the network you could include more methods to find outliers and to find and reduce error propagation in the network, which is not done here. But there are many methods to do that, right? Whole GIS and topology and so on is full of these methods, right? And ways to reduce error propagation. So there is a whole set of ways you can do to do that. So it is not, does not make the method in itself invalid. It works also well in this implementation I used here, and could have taken more care about that. Okay. All right. So, but that's stun, how stun works. Okay, then we have PSP, which is the persistent scatter pair interferometry. Again, it is my understanding of PSP that it also has no APS estimation, but we are starting with a dense network of all PS points already. So in PS INSA and in stun, we are starting with a sparse network. We're just taking the best points, not all the points in the beginning to form the first network or to estimate the atmosphere. We are just taking a subset of points. While in PSP, we directly do all points. And then we just unwrap along this dense network of all points and estimate and unwrap along this network. So it's, in my opinion, similar to stun, just starting with all points in the beginning. Main difference, I would say, I would explain that that PSP is the younger method, right? So nowadays you can do that with your computer. You can, easily connect millions points in the network and unwrap and estimate along them. While I think that is 20 years before, when PS INSA and stun also around that time has been developed, it was important also from computational point of view to not connect all points, you just connect the best points, because I think you couldn't handle a network between millions of points at that time as easy as we can do it now, right? So it is just a further development of that, and also having just following the connections along the line, not really estimating the atmosphere. And I'm pretty sure the PSP has also very good methods implemented to avoid propagation errors and to avoid these problems that you have if you base it all on a network of points. But if you do that well, if you follow them well throughout your network, if you have ideally also different layers of the network, then you can do that quite well, and just then compare these pairs along the network and follow and unwrap along the network. And then you do not need to have an APS estimation at all. Okay. All right. Then we have STEMS. STEMS is the Stanford method of persistent scatters. It bases GPS on phase stability. We estimate the height of the points separately. So when we talk on PS INSA, we estimate the height and the velocity together in one set of equations. In STEMS, this is separate. So we estimate the height first, remove the height, do then ideally a 3D phase unwrapping. Is more like a 2.5D phase unwrapping of the deformation phase. And that allows us then to have a model-free deformation. So in STEMS, we do not estimate, for example, a linear deformation. We can get our deformation free of any model. However, if you want, it's also not free of any model. So in that case, the deformation is estimated to be related in space. All right? So it is estimated that from one pixel to its neighbor, because we are unwrapping it also in space, it is estimated that from one pixel to another, the deformation is not changing too rapidly, right? So that it is slowly changing in space, so that we have a relation of the deformation in space. And in that way, we can then process without having any kind of deformation model. Right, good. So STEMS, to understand that, has been developed for volcanoes. Okay, so in volcanoes we find many points which are phase stable but maybe not have a high amplitude. So that's why we separate that, have a different method to find more points on volcanoes. And if you're interested in volcanoes, we cannot have any deformation model because there is no linear deformation or anything that we can model going on. However, if you're looking at volcanoes and the motion and deformation of volcanoes, they're related in space. So the volcano is, the uplift on one side, or the magma coming in the magma chamber. That chamber is uplifting. That is a deformation that is related in space. So we're going to have a center with more deformation, and then the deformation is slowly reducing on the side. So they are forms that are related in space. You don't really have sharp lines, sharp edges of deformation. So for that, it is working very well. Right? That's what it is developed for. STEMS itself is, I would say, most probably, I'm pretty sure, it's the most commonly used method for processing PS inside. The reason is very simple. The reason is that it's freely available. Okay, so you can download it and start working with it. And it has no need for a deformation model, so that's also good. And it gives you quite good results generally. Right. So, but the problem that we have is deformation is estimated to be related in space. That can be a problem if you're looking at deformation that are not related in space. So, for example, if you're looking at a landslide, if you have a landslide, you typically have painted here some landslide motion, okay, and there is a strong gradient here at the edge of the landslide. At that part here, typically you do not have a relation of the motion in space. You have a jump in the motion. In landslide, that is quite typically that you have a strong difference between motion inside the landslide and outside of the active part of the landslide. So the deformation that you have then is not related in space. And what happens then in STEMS, typically, it's not a huge problem, okay, because typically you're gonna detect the landslide. What is happening that you underestimate the speed of the landslide, okay, because what's happening is then you're assuming a slowly increasing gradient of the landslide, but you have a jump, so you get a phase unwrapping error at that jump, and you're underestimating the motion here. It's a typical error for STEMS. For many applications, it doesn't matter, because typically it matters mostly that you identify the landslide, and as long as you're aware that you may be underestimating it, it is but you still can, analyze that and warn people or make your motion maps or whatever you want to do. Just be aware that there's a good possibility of you underestimating motion. Also here, in that case, we see actually, if we zoom in, if we change the color scale a bit, I use the same color scale for, we see the motion here also identified clearly in stems, but also underestimated around the Las Vegas Convention Center here. Again, not surprisingly, here again, because it's also a very small scale motion. STEMS is not really great at finding those. All right. Okay, now, next time we are talking about distributed scatter-based methods in the beginning, and then I think we wrap it all up and discuss about the overall problems, probably going back on that. But let me stop here before we come to the DS-based methods. These are the probably now the most advanced methods. And also very, very interesting. So please come back tomorrow, right, when we talk on how to fix that issues, what we can do outside of urban areas. Now we have with stems, we have a method on volcanoes outside of urban areas, and we have still stable points with no vegetation or very less vegetation. But what can we do with vegetation? These are then the DS-based methods. We'll talk about them next time. Good. Sishan, do we have questions so far?
Yes, Professor. We have 2 questions today.
2. Okay. All right. Then let me stop here.
Yes, you. Can you see screen?
Okay. 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 All right. I think I have 4 minutes. I can answer them all today. That's making it easier. Why setting an optimal master scene for DS analysis? Yeah, I will show you next time. Okay. We will talk about that. Okay. I had to stop here now for time. But that is an important part of DS analysis, and they have then different kinds of connecting them. So I will not answer that next time. I will show you by continuing the lecture next time. Will the step of PS processing be the same for ALOS, Pulsar, and Sentinel-1? Yes. So that is the same. The general steps, the general processing is the same for all of the different data sets. And can APS be run in Snap Toolbox? No. Snap, to the best of my knowledge, is only doing INSAR processing for PS INSAR and multi-baseline methods. I think you have to switch to another tool. Snap is, I think, now is integrated with stems. I think you can use Snap to process and then move forward, for example, towards stems for PS or multi-baseline processing. All right, and how can the 2 methods be integrated, PSI and DS? That's a great question. That is the method called squeezer, which is the last point of the DS-based processing I'm going to present you tomorrow. Okay, so I'm going to show you tomorrow how we can integrate that. And that is the goal of the, I guess, the most advanced processing method, is a so-called squeezer. All right, so thank you all for joining me today. We have one more session tomorrow, directly tomorrow, where we talk on the DS. That's not going to take the whole day tomorrow. So I think I'm going to recap a bit and maybe connect some dots that are unconnected. They have to think a bit what they're going to do tomorrow then. But yes, so first of all, we are talking about DSE tomorrow. Okay, so thanks for joining. Have a good day, have a good night, and I hope I see you all tomorrow. Bye.
Bye, Professor. Bye, organizer. Thank you so much.
Bye, Professor.
Thank you so much, Professor.
Thank you, Professor. Bye-bye.
Thank you, bro. Okay, everyone.
Thanks, bro.
It's time to finish.
Thank you so much. Thank you.
Thank you so much, Prof.
You're welcome. Okay. So have a nice day. Bye-bye. Take care.
Bye-bye. Bye-bye, sir. Thank you.
Bye-bye.
Record.